Hi, this is Mr. Adams from Midwood High School, and this is a video on how to use the mole. We're wrapping up stoichiometry. We have a test on coming up on Monday, so hopefully this video will be a help. Alright guys, in this first chart here, I have what we've been talking about before. We're going from grams to moles, we're going from volume to moles, we're going from particles to moles. Now you have to, folks, you have to memorize these conversions. If I'm going from grams to moles, I need to use the formula mass or the GFM. If I'm going from volume of gas at STP to moles, I need to memorize the 22.4 liters. That will help take us there. And if I'm going from particles to moles, we need to know Avogadro's number. Okay, now notice that we have A's in all of these boxes. Now what are we doing? We are doing a conversion between one substance. That substance is A. So I know there's many ways we can do conversions. We can convert between one substance. We can convert between two substances. So guys, we have to read the questions carefully. If you're converting between just one substance, you use this chart, okay? And you're good to go. Alrighty. So as always, map the journey. And what do we mean by that? Look at what the question is giving you. Look at where you're trying to go in terms of the question. What are you trying to find? And follow the map and go from there. Don't do too much. Don't do too little. Do what's needed. Okay, so we're moving on. Now, we have an example here. How many moles, okay, are in 44 liters of carbon monoxide? Now, this question right here is obviously between one substance, right? Now, we have our map again over here, okay, and the substance is carbon monoxide. So we have carbon monoxide all over the place, all right? Now, the question is, what are we going to use? Which one we're going to use, okay? We are not going to use everything, folks. We look at the question, it's asking us to find how many moles, so we're interested in here, right? And it says 44 liters of carbon monoxide. So liters, volume of gas at STP, we will look at the situation right here. So we're interested in converting from here to here, okay? We are not interested in particles. We are not interested in grams right now, okay? Now, the funny thing is, what we can do, guys, is this. We can create a shortcut. Because if these two guys are equivalent, and these two guys are equivalent, we can say these two guys are equivalent. Alright? We can say these two guys are equivalent, or these two are equivalent. So it's all equivalent all around. So what I'm trying to say is this. We can set up a ratio between what we're looking for and liters. So what we're given, folks, we're given 44 liters. And so where does that go? Yes, that goes on the outside. We're going to put 44 liters of CO on the outside. Okay? We are trying to find what in this problem? Okay? We are trying to find moles, right? So we're going to put moles of CO on the top. Anything we're looking for goes on the top, all right? Now, obviously, from experience, we need to cancel out the liters of carbon monoxide. So we're going to put liters of carbon monoxide in the bottom, okay? Now, the value that we're going to use in the bottom is right here. So we have to memorize that value. It's going to be 22.4. Okay, 22.4 goes in the bottom. And 22.4 liters of any substance in terms of gas at STP is always equivalent to, yes, 1 mole. Okay? The liters of CO will cancel. 44 times 1 is, yes, 44. And you divide that by 22.4. Okay, so let's do that. Okay, got my calculator here. Alright, what is it? It's 44 divided by 22.4 gives us approximately, on my calculator, 1.96, okay, roughly, moles of CO. Okay, and I'm done. Now I have another question here in my handwriting, so I'm going to dictate how many grams are in 10 liters of nitrogen gas at STP. You can pause the video and we'll go over it together. Okay, we're looking for grams, okay, and we're given liters. So what we're going to do, guys, we're going to put our 10 liters of N2 on the outside. This is 10 liters of N2 on the outside. Okay, we'll set our conversion factor up. We want to get rid of liters of N2, so we put it in the bottom. Okay, we're looking for grams. Now notice I'm using a shortcut. Normally we would have changed the liters to moles and then moles back into grams. But what we can do here, folks, because of all of these guys being equivalent, all right, we can do a shortcut. We can say 22.4 liters, okay, of N2 is equivalent to, okay, the GFM of N2. Okay, the GFM of any substance is equivalent to 22.4 liters of that substance. Okay, in terms of gas. All right, so what's the GFM of N2? You look on your reference table. I see that N is 14.0. So if it's N2, I'm going to multiply by 2, and that should give me 28. All right, so I have 10 times 28, which is going to be 280, right? And 280 divided by 22.4. Okay, I'll clear that. 280 divided by 22.4 gives me 12.5. Okay, so you're working along with me, guys. You have your reference tables. I got 12.5 grams of N2. Okay, so that's another way we can do this problem right here. If you're converting between two substances, you can use this chart right here. You can see what's equivalent and set it up in one conversion factor, and bam, you're done. Okay, we're moving on. We did mole-to-mole conversions in class, guys. Mole-to-mole conversions are very, 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 very simple. But the thing about it, you need a B word. You need a balanced equation. Okay? Any mole-to-mole type problem, you need a balanced equation. What's a mole-to-mole problem? When you're going from moles of one substance to moles of another substance. Okay? Now, in terms of volume, folks, you can go from volume of one substance to volume of another substance using a similar pattern, using the coefficients, guys, okay? You can use the coefficients to do a mole-to-mole conversion in one step, or a volume-to-volume conversion of different substances also in one step. Now, here's what we got. We have a problem here, all right? It's saying how many moles, or how many liters, by the way, how many liters of water are formed if 40 liters of oxygen gas reacts. Okay, so here's what we do. We're not going to panic. We just analyze it. They gave us 40 liters, so the thing they give us always goes on the outside. So 40 liters of O2, 40 liters of oxygen gas goes on the outside. And we ask ourselves, what are we trying to find? We are trying to find liters of water, right? So the substance water, liters, and water go here, H2O. And we're trying to cancel this out. So we simply put liters of oxygen in the bottom. Good. Let me take a breath. And we say to ourselves, we need some numbers in front of those values in the conversion factor. So what's going to happen is we look at the coefficient right here, the coefficient 2 that goes in front of the water. We look at oxygen. We see that oxygen has also coefficient 2. Okay, that's nice and convenient. Now what's going to happen? The 2's will cancel. The liters will cancel. Okay, and guess what? The answer is also 40 liters of water. Okay, and we can ask ourselves, does that answer make sense? Okay, we're given 40 liters of oxygen. We got 40 liters of water. Look at the balanced equation, people. All right? We look at the balanced equation. We notice we have 2 moles of oxygen right here. We have 2 moles of water right there. So what is the ratio? The ratio is 2 to 2, right? Or 1 to 1. So if something has a 1-to-1 ratio in a balanced equation and you do a calculation, that calculation will also come out 1-to-1, and here we just prove that. Okay, so that's a nice simple question right there. All right, so we're moving on. Now, guys, what we did here on this page, we put everything together. Now, I know it looks confusing, it looks horrible right now, but it's just two basic concepts that we have here, guys. The first one that we did already was this one right here. We know all this already, okay, in terms of one substance, A, and we know all this already over here in terms of one substance, B. And what's in the middle, guys, and what's in the middle in green right here, guys, is a mole to mole conversion. So for a mole to mole conversion, you need a balanced equation. So all we're doing with this chart right here, guys, we're putting two concepts together, okay? How to convert between one substance, okay? And how to convert between two different substances, all right? Okay, so we're going to use this in a question on the next slide. Now, guys, once again, I said think of the mole as Penn Station. If you're in doubt about a conversion problem, automatically, don't panic, change it to moles first, and then see where you can go from there. Okay, just what you should do, though, you should memorize this chart right here, commit it to memory, okay, and ask yourself on each question, where am I starting? Where am I trying to finish up? Okay, and all that we need to know in terms of conversion factors, guys, is here in this chart right here. So that's what I'm asking you to commit it to memory. Okay, so we're moving on. We have a balanced equation. We have N2 reacting with H2 to give us NH3. Okay, and we have a question. How many moles of ammonia, okay, all right, I got a typo right here, are formed, okay, when 60 grams of hydrogen react. Okay, so let's map it out. We are given grams of hydrogen. We want to go through Penn Station, so we're going to change that to moles of hydrogen. And what we're going to do next, we're going to change moles of hydrogen into, yes, moles of ammonia, NH3. So that's our map right there. Okay, so now here's what we start to do. We put our 60 grams on the outside of hydrogen, because that's what we're given in the problem. So always start with what you're given. And we're going to change that to moles of hydrogen. So how do we change grams into moles? Very simple. We're looking for moles, so that goes in the top. So moles of hydrogen goes in the top. Okay? And we're trying to get rid of the grams, right? So we're going to put grams of H2 in the bottom. Okay, we need some numbers. Now, if we're dealing with grams and moles, we need the formula mass, we need the gram formula mass, we need the GFM. So what's the GFM of H2, folks? The GFM of H2 is, yes, approximately 2.0, and the GFM of any substance is always, yes, 1 mole. Good. What's going to happen to the grams? They will disappear. And they're gone. Okay? Now, our problem is not done yet. We just went from grams to moles, right? Our next step is to go from moles to moles. All right? So we're doing a mole to mole conversion now. So we don't panic. We set up another conversion factor. All right? We have moles of hydrogen in the top right here. So we want to get rid of that. We're going to put moles of the same thing, moles of hydrogen in the bottom. We remember we're doing a mole to mole conversion, So we say to ourselves, we need a balanced equation. We have a balanced equation. So we put our moles of hydrogen in the bottom. We are looking for moles of ammonia in the top. Okay, so we're going to put that in the top. So moles of NH3 goes in the top. All right. And in a mole-to-mole problem, we need our coefficients. Okay, for mole-to-mole problems, we need a balanced equation. We need the coefficients from the balanced equation. So what do? We look at the balanced equation. We see for NH3, there's a 2 in front of it. So we're going to put a 2 right there. And for H2, we look in front of it. We see a 3. We put a 3 right there. And we stop. How do we know to stop? we follow our map. Our map tells you when we finish, when we get to moles of NH3, we stop. So we see that the moles of H2 will cancel. We are winding up with moles of NH3. We know to stop right there. We don't have to guess. All right. So what do we have now, guys? We have 60 times 1, which is 60, times 2, which is 120. Now we have 120 divided by 2 times 3, which is 6. So 6 into 120 should give me 20, if I'm not mistaken, right? So 20 moles of NH3 would be the answer. Okay, now here's what I want you guys to do. I want you guys to do this problem right here. I want you to pause the video. I want you to map it out first, alrighty? And then fill in the conversion factors, and we'll go over it together. Okay, the question is asking how many moles of gas are needed to react with, 80 liters of nitrogen gas. Now we're going to say how many moles of hydrogen gas. Okay, this is a typo on my part. How many moles of hydrogen gas are needed to react with 80 liters of nitrogen gas? So you're starting with liters of nitrogen gas. And you're trying to figure out how many moles of hydrogen gas. All right, so pause the video and do the problem. Okay, guys, we're winding down. We are mapping it out first, so we're starting with liters of nitrogen gas. All right. We want to go to Penn Station, so we're going to change liters of nitrogen gas to moles of nitrogen gas. All right. Now the problem is not done because we're looking for moles of H2, moles of hydrogen gas. So we're going to change moles of nitrogen gas to moles of nitrogen gas. All right. Oh, moles of hydrogen gas. Here we go. So that's our final goal right here. Moles of hydrogen. All right. So we're starting with liters. So what do? We look at the problem. We see we're given 80 liters of nitrogen gas, N2. So we're given this. We want to change it to moles. So what do? We set up a conversion factor. Okay. And we set ourselves, okay, like this. We want to get rid of liters, so we put what in the bottom? Yes, we put liters of nitrogen gas, the same unit in the bottom. Okay, we want to change liters to moles, so we're looking for moles. We put moles in the top. All right, let me take a breath. We need some numbers, people, in front of these guys. Okay, so what numbers are we going to put? We have liters right here. Okay, so we're going to use 22.4, right? Remember, we can't forget that number in terms of our conversions between one substance. Okay, we're going to use 22.4 to go from liters to moles in terms of volume of gas at STP. So don't forget that. Okay, cool. And 22.4 liters of gas at STP is equivalent to how many moles? Yes, it's equivalent to 1 mole. Good. All right. What's going to happen? The liters of N2 will cancel. All right. So we've done that conversion. Now we need to go from moles of this substance to moles of H2. So we don't panic. We set up another conversion factor, right? We put a line right here. We now want to get rid of moles of N2. So we put the same unit in the bottom, and moles of N2. All right, it's a mole to mole conversion, right? So we say to ourselves, okay, good, mole to mole, mole to mole. We need the balanced equation, so we're keeping that in the back of our minds. Now our final destination is moles of H2, right? So what we're going to do, we will simply put moles of H2 in the top. So for a mole to mole problem, as we said before, we need a balanced equation, and specifically we need the coefficients from that balanced equation. So we look at H2, we see there's a 3 in front of it, so we put a 3 right there. We look at N2, we see there's a 1 in front of it, so we put a 1 right there. Okay, and we're almost done. We cancel out the N2s right here, moles N2 cancels out. We see there's moles H2 left. We're looking for moles of H2. Okay, and we do the problem now. We say 80 times 1 is 80. 80 times 3 is 240. Now 240 divided by 22.4. Okay, I got my calculator right here. I'm going to do that right now. I'll clear everything. So I got, what is it? 240 divided by 22.4. Enter. That gives me approximately 10.71. Okay, so see if we got the same thing. 10.71 moles of H2. So that's how you can do conversion factors using the mole, guys. Now, once again, what we did, we used conversions in terms of one substance going from one substance to another. In this example right here, okay, we also did conversions going from one substance to a totally different substance, okay? Now, once again, if you're going from one substance to a totally different substance, you need to use your balanced equation, okay? So, and that's, we did balancing equation in class, and you have to commit all these different values, folks, to memory. You got to know the GFM, you have to know Avogadro's number, and you have to know 22.4 liters at STP. Now, once again, hard work per sacrifice equals success. I hope this video was a help. And as always, study, study, study. All right, take care.